Let G be the set x plus yi such that x and y are elements of z, I squared is minus 1. Z is the set of all integers, that is positive and negative whole numbers, including 0. Consider the Venn diagram below. In this Venn diagram we have the set C, which is the set of all complex numbers. R is a subset of that set, Q is a subset of R in turn, Z is a subset of Q. We see the set G here shown crossing the sets R, Q and Z. There are three regions in the diagram that represent empty sets. One of these is a shaded. Shade in the other two. Let's consider the kind of numbers that are inside set Z. These numbers are the integers. So for example, minus 1 is in the set Z, 0 is in the set Z, plus 1 is in the set Z, so is plus 2. All negative and positive whole numbers. It's an infinite set. What about set Q? Z is a subset of set Q, so I'll just draw in set Q. Contains set Z. Q stands for the set of rational numbers. Rational numbers are ratios of whole numbers. So we could write Q like this. We could write it as the set consisting of numbers of the form A over B, where A and B are integers, that means elements of Z. By the way, B cannot be 0 here, because we cannot divide by 0. So we could write the set Z like this. So Z is a subset of Q. Why is it a subset? Well, any integer can be written as a ratio of integers. For example, the integer 2 can be written as a ratio of the ratio 2 is to 1, 2 over 1. So 2 is not only an integer, it is also a rational number. So 2 not only belongs inside the set Z, it belongs inside the set Q. So you can see that any element in Z is also an element of Q. Another example might be minus 4. We can write minus 4 in a number of ways. One way we can write it as minus 4 over 1, or we can write it as minus 8 over 2. We can write it as a ratio of integers. So minus 4 is an element of Z, but it's also an element of Q. Now, there are rational numbers that do not belong in Z, of course. For example, the rational number 2/3. This number is not an integer, so it does not belong inside the set Z. It belongs outside the set Z, but it is a rational number, so it belongs inside the set Q. Of course, these numbers don't have to be positive. Another example might be minus 17 over 5. Minus 17 over 5 is not an integer, so it belongs out here. So numbers like 2/3 and minus 17 over 5 actually belong inside this shaded region here. So I will actually show them inside as examples of numbers that would belong in the region between this oval and this one out here. Well, I won't show them in here because this set is actually empty, as I'll explain in a minute. But we could show it out here, plus 2/3, and we could show minus 17 over 5 as examples of elements that belong in Q but not in Z. Now let's look at the set G. As I've said already, G is the set of complex numbers x plus yi, where both real and imaginary parts are integers. So let's take an example. 4 plus 5i is an element of G, because 4 and 5 are integers. Another example might be minus 3 minus 7i. Another example might be 2 plus 0i. Well, 2 plus 0i is just 2, so we can just write 2 there. We're allowed to have 0i because 0 is an element of Z. 0 is an integer. So x and y could be 0. The number 0 itself is in here. 0 is just 0 plus 0i. So the real and imaginary parts are both 0. They're integers, elements of z. You can actually see that all the integers belong to the set G. Another example might be minus 8, because minus 8 can be written as minus 8 plus 0i. Both minus 8 and 0 are elements of z. They're both integers, so minus 8 must be an element of the set G. So G actually contains all the integers. So the set G contains all of z. I'll get back to that later. Now let's consider what G does not contain. What elements are not inside G? Well, since G consists of complex numbers with integer parts, then irrational numbers will not appear in here. Or sorry, rational numbers will not appear in here. Rational numbers I mean numbers like 2/3 and minus 17/5, those kind of rational numbers. Rational numbers that are not integers. These two numbers will not appear. So this region here has to be empty, just as it says in the question. So the intersection of G and Q, well, not all of Q, but the intersection, well, just to use set notation, G intersecting Q less Z. Q less Z is the region between, in here, the shaded region in here is Q less Z. And if we take the intersection of G with that region, we get the empty set. There are no elements that are both in G and Q less Z. Now let's consider the set R. R denotes what are called the real numbers. The real numbers include the rational numbers, the ones that you've seen already, numbers you've seen already, but it also includes numbers that are not rational, that is, numbers that are irrational, numbers that cannot be written as ratios of integers. The most famous irrational, or one of the most famous irrational numbers, is pi, or probably the most famous irrational number. Pi cannot be written as a ratio of integers. You might have seen 22/7 used for pi. Well, pi is only approximately equal to 22/7. There is no fraction equal to pi. Another example is the number e, and also the square roots of all non-square integers. As a matter of fact, there are more irrational numbers than rational numbers. You might get the impression that there are fewer irrational numbers from this diagram, but that's not the case. So if we look at, say, this region here, it's part of all of this here. So numbers like pi, e, and root 2 belong inside the region I've shaded, but they can't belong in here because the set G consists of complex numbers whose both real and imaginary parts are integers. These numbers are not integers. The number pi can be thought of as pi plus 0i. The number e can be thought of as the number e plus 0i. So all of these are complex numbers because they belong to this larger set C. They're complex numbers with 0 imaginary parts. But the problem is the real parts are not integers. So numbers like this do not belong inside G. So that means that the intersection of G with R less Q, R less Q is this region here. So set G and set R less Q have no elements in common, so this intersection is empty. So this symbol phi is used for the null set or the empty set. So we can hatch in this region here to indicate that it doesn't contain any elements. I've also hatched this in, but Well, this is just to indicate the set, not to say that this is empty. This isn't empty, of course. Don't get confused with this shading here. This shading means this region is empty. Now, I said earlier that the set Z, that is the set of all integers, is a subset of G. So I have some examples here of integers like 2, 0, minus 8. They all belong inside G. Because 2 is just 2 plus 0i, 0 is 0 plus 0i, so they all have the form x plus yi, where x and y are integers. So the set Z is a subset of G. It's a proper subset of G. Proper means that Z is not equal to G. The set Z is smaller than the set G. So that means that this region out here must be empty. So we can shade in this part here. So Z is actually this region here. This is Z. So all the integers are in here. There's nothing here. Here I have another picture of the set Z inside the set G. Numbers like 2 plus 3i belong inside the set G, but they do not belong inside the set Z. Here another example might be minus 4, minus 5i. The numbers in this region out here are complex numbers whose real and imaginary parts are integers, but furthermore the imaginary parts are not 0, whereas inside here the imaginary parts are 0. So the answer to the question are the regions in red, this red region here, and the green region. They're empty regions. There are no elements in them. Insert each of the following numbers in its correct region on the diagram. The square root of 2 is an irrational number. It cannot be written as a ratio of integers, so it does not belong in the set Q. It actually belongs in the set R. It doesn't belong in G either. We showed earlier that this region is empty. I'll shade in those empty regions again. There are no elements in here, and there are no elements in here either. So root 2 belongs between R and Q, and I can put it anywhere, like there. 7 is an integer, so it belongs inside Z. Root 3 minus I is a complex number whose imaginary part is not 0. All numbers are complex numbers, but root 3 minus I does not belong inside R. It does not belong inside G either, because G consists of complex numbers whose real and imaginary parts are integers. Root 3 is not an integer. The real part of this number is not an integer, so it belongs out here. Of course, it's inside the set C. It's a complex number. What about 4 plus 3i? Well, that actually belongs inside G, because it's a complex number with integer values for the real and imaginary parts. 4 and 3 are both integers, so it belongs here. Plus a half is a rational number. It's not an integer. A half plus 2i is a complex number, but you see that its real part is not an integer. It's not an element of Z, so it does not belong inside the set G. It belongs outside the set G. I could put it here. Consider the product A times B, where A is an element of G and B is an element of Q. There is a non-empty region in the diagram where AB cannot be. Write the word here in this region. Well, let's just take an example. A is an element of G, so for example A could equal 4 plus 3i. I'll just use this as an example of an element from G. And what about an element from set Q? I might as well use this here. Q equals a half. What happens if we multiply A by B? Well, we multiply a half by 4 plus 3i. Half times 4 is 2, half times 3 is 3 halves. So we get this number. Notice that both parts of this complex number are rational numbers. And that's always going to be the case. If we multiply a complex number with integer parts by a rational number, like a half, then we're going to get a complex number with rational parts. That the real and imaginary parts will be elements of Q. If you think about it, this number AB cannot be in this region here, because this region here that I'm shading in red consists of irrational numbers. But AB is a complex number where both parts are rational. It's possible that one of these parts could be 0, for example. You know, we could have, for the number A, we could just choose 4. 4 is an element of G. If we just set y equal to 0, that's allowed. We could write 4 plus 0i if we like. Then you can see both of these parts are integer parts, so this number is an element of G. No problem there. And we could say again, let b equal a half. But then a times b is 4 times a half, which is 2. We're always going to get a rational number here. Well, this is an integer, but I mean, we could choose b to be, say, 1/3. In that case, what would happen? Then ab is 4/3. We always get a rational number. There's no imaginary part. The imaginary part is 0. But these parts, both parts will always be rational numbers. But we have nothing but irrational numbers in this region. Numbers that cannot be written as fractions. Numbers like √2 and pi and so on. Notice too that this is a non-empty region. We're interested in the non-empty region where AB cannot be. So we call, well, in the question we write the word here in that region.